Welcome to Understand All. I'm your host, Aslekeir Gairleif. Today, we're embarking on a mind-bending journey into the world of quantum mechanics and Bell's inequality. So buckle up, grab your thinking cap, and let's dive in. Imagine you and a friend are playing a game. You each have a coin, and you're standing back to back. Every time you flip the coins, you always get opposite results. Heads for you, tails for your friend, or vice versa. Every single time. Seems impossible, right? Well, in the quantum world, this is exactly what happens with entangled particles. And it's this bizarre behavior that led to one of the most groundbreaking discoveries in physics, Bell's inequality. But before we get to Bell, let's set the stage. Picture it's the 1930s. Albert Einstein and Niels Bohr are in a heated debate about the nature of reality. Einstein, the father of relativity, believed in a deterministic universe, where everything is predictable if you know all the variables. Bohr, on the other hand, was a champion of quantum mechanics, which suggests that at the fundamental level, the universe is probabilistic and uncertain. The crux of their disagreement? The Einstein-Podolsky-Rosen paradox, or EPR paradox for short. Einstein argued that if quantum mechanics was correct, then two entangled particles could instantly affect each other, even if they were light years apart. He called this spooky action at a distance, and believed it was impossible. Therefore, quantum mechanics must be incomplete. Enter John Stuart Bell, a young physicist from Northern Ireland. In 1964, he published a theorem that would change physics forever. Bell's theorem and the inequality that followed provided a way to test Einstein's ideas against quantum mechanics. Here's the gist of Bell's inequality. In the classical world, the one Einstein believed in, there's a limit to how correlated two distant events can be. But in the quantum world, entangled particles can exceed this limit. They can be more correlated than classical physics allows. If an experiment could show this excess correlation, it would prove Einstein wrong and vindicate quantum mechanics. But how do you test something so abstract? The answer lies in the polarization of light. By measuring the polarization of entangled photons at different angles, physicists could put Bell's inequality to the test. The first major breakthrough came in 1982 with Alain Aspect's experiments in France. Aspect and his team found that entangled photons violated Bell's inequality, just as quantum mechanics predicted. But there were loopholes, ways that skeptics could still doubt the results. One loophole was the detection problem. What if the detected photons weren't representative of all the photons emitted? Another was the communication loophole. What if there was some hidden signal telling the particles how to behave? Closing these loopholes became the holy grail of quantum physics. It took over 3 decades, but in 2015, a team from the Netherlands finally succeeded. They conducted a loophole-free Bell test, confirming the predictions of quantum mechanics with unprecedented rigor. The experiment, known as the Delft-Bell test, used 2 diamonds with nitrogen vacancy centers to generate entangled electrons. These electrons were separated by over a kilometer and measured using high-efficiency detectors. The results? A clear violation of Bell's inequality. According to the lead researcher, Dr. Ronald Hansen, the Delft-Bell test closes both the detection loophole and the locality loophole simultaneously for the first time. Source: Nature, 2015. So what does this mean for our understanding of reality? In short, it means that local realism, the idea that particles have definite properties independent of measurement and can only be influenced by their immediate surroundings, is dead. The universe is fundamentally non-local. Entangled particles can indeed affect each other instantaneously, even if they're on opposite sides of the galaxy. This is a hard pill to swallow. It goes against our intuition about how the world works. But as physicist David Mermin famously put it, if you think you understand quantum mechanics, you don't understand quantum mechanics. Source: Physics Today, 1985. But the weirdness of quantum mechanics isn't just a curiosity. It has real-world applications that are transforming technology as we know it. Take quantum cryptography. By using entangled photons to transmit encryption keys, quantum cryptography can guarantee secure communication. Any attempt to intercept the key would be instantly detectable, thanks to the principles of quantum mechanics. Companies like ID Quantique in Switzerland are already offering commercial quantum cryptography systems. According to a market research report, the global quantum cryptography market is expected to reach $1.3 billion by 2026. Source: Markets and Markets 2020. Then there's quantum computing. By harnessing the power of entanglement and superposition, quantum computers can perform certain tasks exponentially faster than classical computers. This has huge implications for fields like drug discovery, financial modeling, and artificial intelligence. Tech giants like Google, IBM, and Microsoft are all racing to build the first practical quantum computer. In 2019, Google claimed to have achieved quantum supremacy with its Sycamore processor, which performed a calculation in 200 seconds that would take a classical supercomputer 10,000 years. Source, Nature 2019. But it's not just about speed. Quantum computers can solve problems that are practically impossible for classical computers. For example, they can efficiently simulate complex chemical reactions, which could lead to the discovery of new materials, drugs, and catalysts. They can also optimize complex systems like traffic networks and supply chains. The possibilities are endless. Other quantum technologies on the horizon include quantum sensors, which can make ultra-precise measurements of gravity, magnetic fields, and time. Quantum networks, which can connect quantum computers and sensors across vast distances. And quantum simulators, which can model complex quantum systems that are beyond the reach of classical computers. But as we stand on the brink of a quantum revolution, it's worth pausing to reflect on the deeper implications of Bell's inequality and the quantum weirdness it represents. For one, it challenges our notions of causality and free will. If particles can be instantaneously connected across vast distances, what does that mean for our ability to make truly independent choices? Are we all part of some vast cosmic entanglement? It also raises questions about the nature of reality itself. Is the universe deterministic or probabilistic? Is there an objective reality independent of observation, or does the act of measurement create reality? These are questions that have haunted physicists and philosophers for decades, and they're far from settled. But perhaps the most profound implication of Bell's inequality is that it hints at a deeper level of reality beyond what we can see and touch. A reality where the rules of classical physics break down and the impossible becomes possible. A reality that, in the words of physicist John Wheeler, is stranger than we can suppose. As we continue to probe the quantum world and unlock its secrets, one thing is clear: the future is quantum, and it's going to be a wild ride. So the next time you flip a coin, remember Bell's inequality and the quantum weirdness it represents, and marvel at the fact that, at the most fundamental level, reality is not what it seems. And that's our journey into the strange and fascinating world of Bell's inequality. I hope you've enjoyed this quantum adventure as much as I have. Remember, the universe is full of surprises, and the only way to discover them is to keep asking questions and pushing the boundaries of what we think is possible. So stay curious, keep exploring, and always remember, in the quantum world, anything is possible. Until next time, this is Aslekeir Gairleif for Understand All. Keep questioning reality.